Okay, then we talk about completing the square. Like, because there is this formula that is being used by many teachers. I heard Hunter was saying his teacher is using this formula to teach completing the square. These formulas don't make sense to me because I don't see any square here, although we are dealing with completing the square. We don't complete any square here if we are just using the formulas. We just plug the values of A, B, C in the formulas that you have to memorize and be able to turn this quadratic equation into a vertex form, which looks like this. And there's D, there's a formula for D, there's a formula for E. You just plug them there. So let's make sense really what completing the square means. So we can use algebra tiles again to model expression. So here we have x squared plus 6x's in 5 ones, where here a is 1. So I will rewrite the formula by considering the value of a is 1. So this is the new formula for completing the square. My goal is to build this formula from conceptual understanding. So I will show you why D is the half of B, which we already taught as we are presenting our work. And I will show you why E is whatever it is, like C minus the square of half of B. To do that, we can simply give these tiles to students and ask them to create a square out of these materials. So the goal for a student is to move these tiles in order to create a square. As we all know, the sides of a square should be the same. So if I have 6 x's here, so I should split the x's in half so that I can start creating a square here. And I can rewrite the x term as 2 times 3x, because that's how I started creating a square, right? So I just rewrite the equation. It's still the same quantity. I still have x squared. I have 2 times 3x, which is 6x's, and I have 5 here. And we split the x term in half. So I can make sure at this point, students understood this as a procedure, because we always split the x term in half. Before even we get to the formula, I am developing the procedure with students. We always split the x term in half, and x term referring to the b in the formula. But I don't have a square. I still don't have a square here. So in order to complete this shape into a square, I need to fill in this space. I can either use what is given, put it there, or what I can do is I can add 9 zero pairs. So I'm not touching my original quantity, 5. What I'm doing is I'm just adding 9 ones, positive 9 ones, and negative 9 ones. I am doing this because I don't want to change the original quantity. I added things, but I still have x squared plus 6x plus 5, because these new things, when you add them up, it's 0. So that's why they are called zero pairs in algebra tiles. When you have different colors in algebra tiles, they are called 1 yellow and 1 red. They are called zero pair, because 1 positive, 1 negative makes 0. So I basically added 9 zero pairs in order to not change the value of my original quantity. Then what I did here with the tiles can be modeled by using this algebraic expression. You can see x squared is right there. 2 times 3x, my original 6x is here. And now I added 3 squared and I subtracted it. Like I added 9 and subtracted 9. So I didn't change my equation at all. And why I write it as 3 squared, because you can see this side is 3, this side is 3, so there is 3 squared, but there is 9 ones here, and there is 9 negative ones here. And this 5 refers to my original 5. Okay. So at this point, I should support my students to see that the term I added is always the square of half of p, right? Always the term I added is going to be, because this is 3, which is half of p, my b was 6. The term I added is going to be always the square of half of p. So as a procedure, students should see we always split x term in half from the previous step, then square its coefficient. Okay. Now you would note that these 3 terms can be written as x plus 3 squared, right? Because that's the square that we built here. You can see these terms refers to my whole square, which has a side length that is x plus 3. So the area should be x plus 3 squared. And then I just rewrite what is left. So negative 9 plus 5. So I can turn this expression into a vertex form by just reorganizing the algebra tiles, adding, subtracting, adding 0 pairs. So this is how we can form this original expression into its vertex form by completing the square. That's one example that you can do with students. You can do one more time with different numbers. Another example. Then you can generalize after you repeat this process a few times with different quadratic equations with different numbers. You could develop this formula or support your students to make sense of this formula from their experience. For example, in general terms, we have x squared plus bx plus c when a is 1. Through our experience, we learned that we always split the x term in half. And I rewrite the general term by applying what I learned. So we can apply this procedure, splitting the x terms in half into the general equation like this. Through our experience, we also learned that we square its coefficient, right? Then I'm going to square its coefficient. We can now apply this procedure into a general equation like this. We are basically adding the square of half of p and subtracting the square of half of p. Then I can rewrite this expression as x plus b over 2 squared, because that's my original square. And what's left over can be seen in this way. And that directly tells me the formula. So d is basically b over 2. And what is left is going to be e. So this is the way we can teach completing the square. We are starting with algebra tiles, developing meanings, then build procedural fluency, build formulas later.